Hello ladies and gentlemen, welcome to Chapter 4, Video 1. Today we're going to talk about what exactly are forces, and along with that, what are free body diagrams. So, what do we want to look for in this video? Well, what we want to look for is, first of all, what is a force? When we talk about a force, what's that mean? Second of all, what units are used to measure forces? We've had units with all of our other quantities. Velocity had meters per second, acceleration meters per second squared. What are we going to use for forces? Third question, what types of forces exist? Is there only one type of force? Are there multiple? We'll take a look at that. And finally, what exactly is a free body diagram? Why do we use them? What's involved? We'll look at that as well. So, let's start off at the top. What is a force? Well, anytime we talk about a force in physics, what we're talking about is some sort of push or pull on an object. When you push on a door, for instance, to open it up, you're exerting a force on the door. Or maybe you have, a string that you're pulling on. For instance, maybe you have a box that you're pulling on with a rope. That's exerting a force as well. So anytime you do a push or pull, that is a force. Some things with forces, they are vector quantities. Remember, a vector has a magnitude and a direction. Well, a force has a magnitude. There is a size to it. And it also has a direction. You're going to be pushing north, or maybe pushing horizontally, pushing left, pushing right, whatever. So size and direction still matter. Forces are vectors. And the key thing with the force and what we're going to be looking at and how it ties into what we've been doing is, in certain situations, forces can result in an object changing its motion, which means there's an acceleration going on. So that's going to be something we're going to look forward to later on, is that forces can cause acceleration. So those are the key things we want to know about a force. It's a push or pull. It's a vector. They can cause accelerations in certain instances. Those are the key things. Now, when we talk about a force, we want to have the unit with it. And in the SI system, the unit of force is measured in a unit called a Newton. And we're going to talk about the idea of Newton's laws of motion. They came from Sir Isaac Newton. We'll get to that in the next video. But that's kind of why we call them Newtons. They're Newtons because of Sir Isaac Newton, who contributed a lot of ideas into motion. So forces are measured in units called newtons. And the way it works is we say 1 newton of force will accelerate a 1 kilogram mass at a rate of 1 meter per second squared. So what we do is we say, okay, 1 newton is equal to 1 kilogram meter per second squared. We'll look at those units a lot more in the next section when we talk about Newton's second law of motion and an equation we'll use. But that's the general relationship. 1 newton is 1 kilogram meter per second squared. Now, there are, of course, other units we can use. In the CGS system, centimeter gram second, they use what's called a dyne. And the one we use in terms of what we use here in the United States is pounds. Pounds is a unit of force. Whenever we exert a force on something, we'll say, oh, there's 10 pounds of force on that. Well, we can identify the relationship between pounds and newtons in the sense of 1 pound is actually 4.448 newtons. Or if you flip it around, 1 newton is 0.225 pounds. So something you could think about is, if you ever hold from McDonald's a quarter pounder with cheese, that weight there is 1 newton of force. So a newton is about a quarter pounder with cheese. We can call it that way. Now, along with that, we can identify some types of forces. And there's a variety of forces that we're going to be talking about throughout this unit. But in general, we can classify forces as one of two things. Either contact forces or field forces. Contact forces are probably the ones we're most accustomed to. And they're forces that exist whenever there's physical contact between objects. When you touch a doorknob, you're exerting a force on the doorknob, or kicking a ball, or throwing a ball, or pulling on a rope. All of those forces are contact forces. They happen because there's actual contact between the two objects. That's easy to observe. The harder one to think about, in terms of they exist but they're very hard to see in some cases, are what are called field forces. And field forces are forces that occur between objects, but they're not actually touching. They're at a distance. And there's two very common ones we can think about. Gravity is one of them. Anything that is massive, it has mass to it, exerts a gravitational field. We're going to be talking more about that later on. For instance, the Earth, the Earth exerts a gravitational force on us, and this can happen whether we're touching the Earth or maybe we're far away. In both cases, there's this gravitational force acting on us. Magnets. We know magnets can exert forces on each other, and they don't actually have to touch. You know the idea of North and South Pole. They'll start attracting each other and kind of pull together so that they meet. They're not actually touching. They can exert those forces far away. So we can classify forces as one of those things: contact forces or field forces. Now, if we want to get really technical, what we can say is that there really aren't any contact forces. What we can really say is that all forces that exist in nature are really field forces. It's just a matter of how they interact at a microscopic level, and that's what's causing the contact force. What's happening is, for instance, when you touch something, the atoms at the microscopic level are exerting these field forces on each other. It turns out that if you have charges that are the same, they like to repel. And as a result, you're not actually touching, it's just that the force you're feeling is from those charges pushing away from each other. But again, that's getting really, really nitpicky. We're not going to be too concerned with that. Just know that, if you touch something, there's a contact force, and if there's no touching but there's a force in there, it's a field force. Now, we can also get more nitpicky and classify forces based on what are called the fundamental field forces. And there's 4 of these forces here. The first one is the gravitational force. That is the force of attraction between any 2 objects with mass. Like I just said in the previous slide, that the Earth exerts a force on anything around it. Same thing with the Sun. That's what keeps the planets in orbit. You have the gravitational force of the Sun pulling on these planets as they move, and that's keeping them moving in their elliptical orbits. Second type of fundamental field force is called the electromagnetic force, and that is the force of attraction or repulsion between charged particles. And they can be atoms, molecules, or just particles in general. In chemistry, we probably talked about, protons and neutrons and electrons and how they have charge. Well, it turns out those charges can interact and exert forces on each other. A third type of force is called the strong nuclear force, and this is the force inside of an atom that is responsible for keeping the nucleus together. You have all those protons and neutrons together in one bundle, and since protons are positively charged, they all want to fly away from each other. The strong nuclear force keeps them together. On the other hand, you have the weak nuclear force, and that's responsible for radioactive decay, which is where you actually have these smaller chunks of the atom kind of flying out. So there are field forces in nature that exist, and they're actually responsible for all of the forces we encounter. Generally speaking, the gravitational electromagnetic forces are the ones that show up the most in terms of what we're going to be talking about. Alright, so that gives you some idea of the types of forces that exist. Let's talk about what we can do with it. All we want to do right now is focus on identifying the forces in terms of a drawing, and that's what's called a free body diagram. These are going to be very, very helpful moving forward. And a free body diagram is nothing more than just a picture that shows how all the forces act on an object. We want to identify the forces that influence an object's motion, and based on that diagram, later on we're going to actually take that diagram, analyze it, and identify some features about the motion. Is it accelerating? If so, which way is it accelerating? And some other things as well. So to draw a free body diagram, here's what we do. The first thing we do is we can draw a sketch or a dot. It depends on how creative you want to get with this. You've all seen my drawing skills in class. You know I can't draw, so I generally use a dot for these. If you want to get really fancy, feel free to draw the object itself. Then we're going to draw force vectors on our sketch. And here's how it works. We know with vectors, the arrow points in the direction of the vector, and the size of the arrow is proportional to the size of the vector. So if it's a very large force, we're going to draw a very large arrow. Small force, small arrow. And again, it should point in the direction of the force. So we're going to draw these arrows on our diagram. We're also going to assume that all forces act at the center of the object. Now, that isn't necessarily true in nature, but for simplicity's sake, we're going to assume that for now. And then the other thing we want to do is, if we know the name of the force or the value of the force, or both, we want to label those as well. So let's take a look at how this works. Let's say we have a bird feeder, and there's two forces acting on it. We have a 25 Newton downward force due to gravity and a 25 Newton upward force from a chain attached to the bird feeder. That's holding the bird feeder up off the ground. We want to draw a free body diagram. So first thing we do is draw our picture. In this case, we have a nice lovely little rectangle with a triangle on top, and we're going to draw in our forces. First thing I see is, okay, there's a 25 Newton downward force. So I would draw that in. Notice we start at the center of the object, draw down, and I'm going to label it F grav for force of gravity. And I know it's 25 newtons, so I'm going to draw that on there as well. The other force I have is a 25 Newton upward force. So I'm going to put that on there. And again, start from the center of the object. It's equal in magnitude, so I'm going to try and draw the arrows to be the same length. And I'm going to label it. In this case, I'm going to call it F chain for the force of the chain. And again, that's going to be 25 newtons. So there's one example. Another example we could say is, let's think about like a banner. You know, for instance, maybe you're hanging a banner in the school that says congratulations, or, you know, 12th graders can leave now, who knows. So the banner has a couple forces acting on it. In this case, we have a 10 Newton downward force due to gravity and two 14 Newton forces directed at a 45-degree angle above the horizontal in opposite directions due to two strings. So you can think of it as, you know, we have this banner. There's these two strings kind of pointing upward and to the left and right. They're supporting the banner. And then there's the weight of the banner pulling it down. So we're going to draw on the forces. First thing, 10 Newton downward force. Except, here's my error for the video. You'll find all my videos have errors in them. In this case, it should have been 10 newtons downward, not 25. And then I have my 14 Newton forces at 45-degree angles. And there they are. Notice that if it is at an angle, you want to put in the angle as well to identify that, hey, it's not exactly in a straight line, it's at an angle. But you notice, again, I labeled them all. F string, both of those are 14 newtons, 45-degree angle. And notice I did actually fix it here. It is now 10 newtons downward. But that would be my free body diagram. Okay, so when you draw a free body diagram, you need forces in terms of you need an arrow. Try and get the lengths to be, you know, proportional to the size. Label them with a name, and if you know the value, give the value. Alright, so to wrap up this video, we go back to our guiding questions. What's a force? A force is a push or pull on an object. It is a vector. That is the key thing we're going to come back to later, because when we look at adding these forces together, we need to do vector addition. So that's going to be something to consider later on. What units do we use to measure forces? Forces are measured in newtons, and 1 newton is 1 kilogram meter per second squared. What types of forces exist? Well, the types of forces we have are, we have the contact and field forces. We said those were kind of the two broad categories. And if we want to look into the specifics of the field forces, we have the gravitational, electromagnetic, strong nuclear, and weak nuclear forces. And then finally, what's a free body diagram? It's just a picture that shows all the forces acting on the object. They have names, maybe they have values, but it shows what forces are acting on it in what directions, and it's going to help us analyze the object later. In our next video, we'll be looking at Newton's laws of motion and talk about how forces can actually affect the motion of an object. I'll see you in class.